It's
Um,
funny that the int tag will let it do whatever it wants. And this is a little bit of a Dungeons and Dragons joke for my fellow
oh
nerds
yeah,
out there.
nasal
But
dragons, exactly.
the wizards are the int casters, the intelligence casters, and they're also the most dangerous. So that's great that that's how this works. I'm Ken Briota, editor in chief of Embedded Computing Design. I'm very excited to have as my guest today Rolland Dudemaine of Trust in Soft, and we're going to be looking at their really exciting debugging platform for C, C++, and Rust. Is that right, Rolland?
That's correct. Hello, Ken. Happy to be with you. Indeed, we're going to focus on software verification, and especially from the cybersecurity angle, but not only.
That's super exciting. Obviously, this is critical infrastructure for any embedded piece of software or even hardware as those two worlds get ever closer together. So I know you've got a couple of slides to introduce us. Why don't we jump right into those?
Right. So when you look at the problem that are remaining in the world on regarding cybersecurity and in general robustness of software, we're not the only ones to say that there are still a lot of runtime errors remaining. People have been testing stuff and they know how to verify that the software works as intended in general. However, there are always things that remain that may cause robustness issue on the long term, or getting hackers a lot of fun to actually have security problems. If you look at the studies from Mitra, what they say is that actually the vast majority, 70% of those vulnerabilities remaining actually are runtime errors. That means buffer overflows, incorrect pointer handling, incorrect calculations, and finally, all of those in terms of memory safety are at the source of the arbitrary code execution, which is really taking over the system.
Oh.
So how do you actually find those? Well, testing helps. But then in the cybersecurity industry, recently they've been doing a lot of what's called fuzzing. And when you do fuzzing, you basically try more cases, and more cases. But that still goes into just the hundreds of thousands or the millions of tests. And that still doesn't get you a guarantee that you can verify all the values. Plus, you need to couple that with sanitizers to try to find some elements. Trust in Soft Analyzer or TIS Analyzer actually takes a different take and allows you to simulate your software in a controlled environment and give it precise inputs, specific inputs with specific values, like you do with fuzzing, but also take a different angle and just give basically the whole range of possible values as inputs. The consequence is that you can actually verify that the entire software is verified with all the possible inputs of whatever is possible for your application. So at least you verify that nothing ever goes wrong on any path of your software. So if you look at the solution that we provide, then it's actually a complete environment. There's a project manager that's graphical to be able to configure the analysis of your software. Then the analyzer core itself is command line driven or can be run in CI. It's actually designed to run in CI. But when you find issues, when you find alarms, or you be undefined behaviors, then you can investigate them with the root cause investigator. And then, of course, at the tail of it, you can produce a report for QA. All of this is actually based on a core analysis kernel that is based on formal methods. That's important because that will give you the guarantee that it will find all the bugs that it searches for, and even go, if you go to the end of it, to guarantee that there's nothing left, which is something very few tools can provide actually.
It's
And if you,
interesting.
yeah.
Sorry to interrupt. I just wanted to say that it's really interesting because the first time I saw this was at Embedded World this past year. I got a chance to take a look at the analyzer, and you were saying that this is functional for C, C++, and now for Rust. That's newer, right?
That is true. Thanks for the note. Actually, the previous slides were updated for Rust, but this one I missed. It does say C and C++, but actually it does cover Rust. Right now, we're capable of doing service on the Rust side, because TrustInSoft can also do the analysis for you if you want to. And the tool will be available in October.
Incredible.
For Rust. What's also pretty unique is that that means with that tool, you can analyze C, C++, and Rust code all combined. So it's not just analyzing Rust code or analyzing C code, but also analyzing the combination of them. And so when you have a mixed world, which is the reality of things, then you have the chance to be able to ensure that the combined integrated software is actually running correctly.
Right.
And all that goes into basically not removing activities from what you have to do, because that's life as a as a developer. But however, to reduce the risk of actually having those expensive bugs remaining later in the game. So using it earlier during development actually can save a lot of effort and money.
Yeah, absolutely. Avoiding rollbacks or having to do updates to remove bugs whilst stuff is out in the field is a huge cost savings and headache solver, honestly.
Exactly, and that's true for all the industries. I mean, obviously recalls can happen in well-known ones, but you don't want a rocket to explode just because you missed a bug.
Right. It
All
turns
right.
out it is rocket science.
Yeah.
Exactly. Awesome.
So let me.
So Roland, I'd love to give the viewers a chance to really see how this works and how Analyzer gets down into the weeds, as it were.
All right. Well, I have a short demo there. So what I'm going to analyze as a piece of code is basically a crypto stack, because that's fun. Crypto stacks are complex pieces of code. They're tough to analyze. They're tough to demonstrate. And if we find bugs in them, then that's exploitable usually. So lots of fun, lots of more fun for the hackers.
I think if in the course of this demo we mine any Dogecoin, we get to become officers of the U.S. government too, which is nice.
Well, no politics for me. All right. So this demo, what I'm going to show is really, it's a straight out checkout of TinyCrypt. So what I'm going to prepare though is I'm going to type a first command here to build and capture the build of all the commands of the build that have been done. Why is that important? That's important because you always want to analyze code in exactly the same way that you build it and you release it. If you don't actually do it that way, then there's a risk that you're trying to verify some code in the code you don't ship, really. So here I've built it, I've cleaned it. The remaining item here is something called compile commands, which is following a standard done by LLVM. And it's just a list of command lines. And what our tool will do is it will take the information that is inside those files, and then auto-configure the files to be built in exactly the same manner. That's enough command line for now. I'm going to switch to the TrustInSoft Project Manager interface, which is a graphical interface here. So I want to create a project because I didn't have anything on that source code. Then I'm going to select that directory here. All right. And that's going to be in TinyCrypt. Then open. I have a compilation database, which we just created. So we can see here that the tool actually found 27 files to be considered in that build. And we don't need to give the list of source files because these are not the entire source files of the repository, but all the ones that actually are built in the code. Then I can type next. Then what the tool does, it's verifying, it's checking that indeed the configuration that was passed in the compile commands is actually reproducible by the tool. And we can see if we click on one file here, you get the functions that it found, the globals eventually, if there's any, and if that failed for whatever reason, then you would get the log and information on how to diagnose that and repair.
So let me ask you, Roland, it looks to me like how the system is working is basically it's running the the various code parts in obviously a safe environment to check and make sure it all runs correctly there. And if it doesn't, you get the error message and you can sort of track that down. Um, is that sort of a pretty straightforward understanding of how that portion is working?
That's perfectly correct. So the way Trust in Soft Analyzer works is it will not actually build or run the software on the target. Instead, it will take the code, make a model of the code, and start with the initial values that are supposed to be in the code, and then simulate each state of the application that is reachable. You could understand that like a simulator, but it's a super mathematical simulator because it will go through all the reachable branches and also consider all the multiple values
Mm-hmm.
of the of the application. And if you give regular values, which are like I'm going to show right now, it will remember each of the values, but you can also give ranges of values, and then it will basically do the mathematical calculation on all the ranges of the evolution of those ranges of value in the application. And
Very
that's how you
cool.
can actually do an exhaustive verification.
So, and this is the show where we get down into the weeds on this kind of thing. So, before we
Exactly.
move to the next section, I wanna ask. I know sometimes with code, bugs originate in what I call phantom code. It's the little snippets that maybe were in an earlier version or were part of an earlier line of code that you ended up abandoning, and it just got lost in the mess of thousands or millions of lines of code, that kind of thing. Will Analyzer also find those little snippets and help you remove them, or if it's not a working part of the code, just skip those and move to completion?
So that's a great question. Because the tool focuses on the behavior of the code, it's not going to care really about the way you code, the coding rules or the shape of the code. What it's going to focus on is what the code you actually wrote will do to the data you give it
Okay,
as input. And the consequence of that, if there's any inconsistent code that's coming in, and it's the usual thing where you, like you say, you create a function, then you add some code, then you remove some code, you add some code again, and suddenly the algorithm becomes inconsistent. Our tool
right.
will again take that declaration as it is finally, and then try to make that evolve, make the data evolve through that code. And if that leads to an inconsistent or invalid value, then it will find it.
Gotcha. Okay, awesome. Let's move forward.
All right. So let's start to create a new analysis here. I have tests in the tools in the source of TinyCrypt, so we can reuse test. If I didn't have test, I could create what we call a driver to be able to test a particular interface. Since we have the luxury of having tests, let's use them. In particular here, no, not this directory, test. We see that we have tests for a variety of crypto algorithm. I'm going to use CMAC just because I know this one is nice. Then for that test suite, the possible functions in that test suite is that list here. We could select just one test. That's one way to do the analysis. I'm going to keep it simple and start from main, and then run the entire test suite for that CMAC algorithm. The tool again found that test. It used that test file that I selected, but it also found all the dependent file correctly there, and then selects it for doing the analysis. So what's nice is that it doesn't consider the entire code base that we provided and we parsed earlier. It actually detected what was necessary, which means that the analysis can be a little bit faster and at least focused.
Nice.
I could optionally do some configuration, but let's start with nothing and leave it like that. However, I will give it a name.
Mm-hmm.
Then create the analysis. We're done with the first analysis, so we can just run it.
Wow. And that was a live run. That it went that fast.
Right. So the running, it's actually always, well, it's 4 seconds, not too bad. And it did find one bug. So one thing you can note is it's not going to be like some of those static analysis tools, which are going to give you 100 bugs or 100 issues. It's actually finding one issue, and that issue is reachable. So it tells us that there's a pointer arithmetic issue. Oh, wait, I need to undo. Well, that's fine. I need to undo a few changes. It wasn't the real thing. Let me undo the changes I did on this file here, and rerun the analysis. That's fine. That makes it real. Let me run the tool again.
That's incredible. We accidentally found a real problem.
So let's see. The first bug I wanted to show is that one. It's an overflow, and actually we're going to solve 2 bugs and then find the third one. So we did find a bug. I don't understand what the code is. I'm not an expert on time decrypt. You're not either. So let's investigate it. I can start here and start the investigation interface. So here, that's opening a new window. It basically runs the analysis again in order to be able to show you an interactive interface. This is officially called the root cause investigator. I like to call it the debugger because that's really how it looks like in practice. And so we can find the same error that we saw before. So if that's readable for you, well, you see here, we have an error here. It's completely focused here, and the original source code is visible on the right side. So when I do that, I can click on A, which seems to be a pointer, and we can see it's a pointer to some symbol that was coming from up in the call. I can keep that one and start looking at the entire pointer value. And we see that actually there were 3 calls. The tool actually observed that we reached key 0, key 4, and key 8. So actually, let's switch to another view, which is not showing you the complete overview of the data, but each state of the data. So now you understand a little bit more that actually what happened is it actually reached the code 3 times. And we see it's a while loop here. What happened is the tool remembers those 3 times. And so we can track that. Let me remove K and look at the pointer here. And we see behind that array, it found at offset 0, it found 43. Behind offset 4, it found 40. And behind offset 8, it found 171. And it seems like the last one is going to be the cause of the trouble. So I can start to use the complete expression that the tool was telling us is causing trouble and look at what's going wrong. So it tells us that, well, yeah, indeed, those 2 first paths were fine, but the third path had a problem, and we see it in red. What is the problem? The problem is the sign overflow. The C language is fantastic. If you look on the right side, we have just the expression here, but on the left side, we see an explicit cast to int. And when you do a cast to int of a value over 128, then that's an undefined behavior. In C language, that means that the compiler can do anything it wants, including doing the right thing, including even discarding the code. And really, it's undefined. And that's a typical example of things that will work correctly when you work in debug. And in debug mode, you don't enable optimization. The compiler will do what you expect it to do. When you enable optimizations, you would expect the compiler to warn you, but it won't. It will actually take advantage of that and then usually get rid of the code or do whatever is most convenient for it.
Right. It's funny that the int tag will let it do whatever it wants. And this is a little bit of a Dungeons and Dragons joke for my fellow nerds out there.
Nasal dragons, exactly.
The wizards are the int casters, the intelligence casters, and they're also the most dangerous. So that's great that's how this works.
Exactly. So what do we do about it? Well, I can allow source code editing here and then cast it explicitly to a non-signed int. And that will actually solve the problem. So I can save that file. And so you see this bug was on K. I can run it again and run the analysis. And now we reach another trouble. It seems like now there's no longer an issue on that line. We solved 1 bug. That's good. But we reach a second bug. And well, I mean, that second bug is exactly the same. You see,
Uh-huh.
it's a class 2 int and a shift to 24. So, well, I'm going to be clever here and then solve the same issue. Seems that like this is subword. It seems like a function call or a macro. There's not macro up there. So probably the solution is to add the unsigned it here. So, well, again, not something very easy to see the first time you understand and you discover the code, but ultimately this is the kind of bug that is pretty hard to find because the 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 typical compiler will not warn you for that. The typical static analyzer will not warn you for that, but it can really bite you later on if you do it wrong. So, well,
Oh, yeah.
anyway.
Very
Well,
cool.
so we solved 2 bugs today. That's good. Is that enough?
3 if you count our accidental bug.
That's true. And then, well, we end up on the one that I was showing earlier. Actually, we have a -1 byte leads to an invalid offset of -1 byte, which is obviously wrong. And if I look at the out pointer, which is apparently the source of the trouble, reading into K1, we do see that there's something going on that could go wrong. And here, that last one would be the source of the trouble. I'm going to stop there because obviously we can dig a little bit, but you can see still that the tool remembers each of the values that were reached, and that's the important part.
Very, very cool.
The second, so okay, let's pretend I've done a lot more work. So I've prepared another project, which is not just one analysis going out of box, but actually doing the same analysis on all the algorithms and doing it entirely. So here I have way more analysis and it's a complete list. We have a number of bugs actually in total. We found those 8 bugs. Actually, I think there's a 9th one, but at least those 8 confirmed bugs here. And that's actually quite frightening for that stack, but it is what it is. After that, what I can do is we can have an overview on the code coverage. We can look at the coverage in a more detailed way in the directories here. And what's nice is, again, because the tool remembers each state of the application, it can provide information about what's going on, and it can store and do a report of the code coverage, which is something that's actually usable for doing a complete audit of code. So here I have a function, for example, and it's clear by just looking at that we did reach these lines, but we did not reach that one. So obviously, if you want to do thorough testing, you want to focus and create new tests for those values there. That's still inside the project manager. At the end of it, I can generate for my QA colleague a report, and that will create an HTML file. Yeah, click. Let me click. Yes, it's there. And then that will show me an HTML file that is actually self-contained. So I can give that to the rest of the team. That will show me the same alarms as before, the same analysis as before, the same coverage information as before, directories, function, line statement, even MCDC if you want. And as a bonus, also for security engineers, search C and CWE compliance here. You can
Very
see
cool.
well. And it's all linked if you want to look at the particular information about this particular CWE out of bounds read. I can just click and it takes me to the public website of Mitra to understand what's going on.
You know, it's funny, Rolland. The actual function of analyzer is very cool, and I know the coders and sysadmins and quality control folks and stuff out there are all going to love that. The fact that it generates reports for you is the real secret sauce here, because I've never met anyone in code who likes writing the reports at the end. So it's
Well, yeah, and also usually reports, even when reports are nice, and I mean this one gives some context and so on, ultimately you need to dig in the code to understand in an interactive way how the code works. So that's why I was
right.
showing earlier the investigator, because interactivity is key.
Yeah, yeah, awesome. Is there anything else that you want to show us today, Rolland?
No, that's it for today.
Amazing. Well, in that case, I'm going to bring us around to the end. And but before I let you go, I just wanted to sort of get you to talk a little bit about Obviously, C and C++ are well understood. They've been around for a long time. Some folks are just now getting into Rust. It's been around for a bit, but it's starting to really grow in importance. I've seen, there's a association for Rust that's been growing rapidly. So I wonder if you could talk a little bit about how the unique problems of that you can bump into with Rust, and how
Mm.
Analyzer gets into that, just for the edification of some of our viewers who might not be as aware.
Yeah. So let's, before I criticize Rust, let me state something. Rust goes a long way into the good direction. So it solves a number of things. And actually, it's funny because what really Rust does at the core is just force the developer to do the right thing. Um, it
Yeah.
basically detects a lot more issues at compilation time, but it's still kind of a static analysis level of finding things. And when the Rust compiler cannot understand what's going on, and there is still a risk of things going wrong, then it will instrument the code to be able to verify it at runtime. And then
Yeah.
when it does go wrong at runtime, then it calls something called panic. Um, on the
Oh, I hate
desktop,
that.
exactly, don't panic. um, so obviously on a PC, in a regular desktop, it may be fine to panic and to have the application crash. You just start it again and move on. In mission critical systems, that's something you can't actually afford to have. So for all those cases that would lead to a panic, you need actually to figure out a way to avoid them in the first place. That can be coding practices, but really that's where our tool can actually bring a lot. Um,
Yeah.
it allows you to again have the analyzer understand how the Rust code would be executed, would behave, because it's all about behavior. It would behave on the target, and figure out those cases which would go wrong. And surprisingly, you'd expect that there are a few of them, but actually, surprisingly, we did already find interesting and important bugs in customer code.
Wow.
So the other aspect of it is what I mentioned earlier is when you're able to do a Rust-only implementation, then your life is somewhat better because you can have good practices on the entire code base. But that's rarely the case. In reality, you have a legacy to deal with. So now the question is, how do you deal with that legacy and how do you deal with the risk? Rust has the concept of unsafe, where basically unsafe is not a bad construct. It's just that you're telling the Rust compiler, I know what I'm doing. I'm taking responsibility.
Yeah.
and,
Yeah.
and so you need, again, something somehow to verify that that unsafe code is safe enough. And that's where the analyzer, the Trust in Soft analyzer, is able to go across the world and then analyze the Rust code combined with whatever is behind.
Incredible. Well, thank you so much, Rolland, for talking us through here. Where can folks find out more about Trust and Soft and Analyzer?
Yeah, thank you, Ken, for the opportunity.
Should people just go to trustandsoft.com to find out more about what's going on with this, or should they find you on GitHub? Where do you guys like to interact?
So that is true. Trust-in-soft.com is the right place. We also have a number of videos on YouTube and a number of and you can find us on LinkedIn. So many ways to contact us. You can't, if you just search for Trust in Soft, you'll find us.
Incredible. And we'll put links to all that stuff down in the video description, of course, for folks out there. Make sure you subscribe to both this channel and Trust in Soft if you haven't subscribed to us. Make sure that you share this video around so that other folks can get a look at TIS Analyzer. And visit embeddedcomputing.com for all the news in the embedded computing space. Again, thank you so much, Rolland, and thanks to Trust in Soft for joining us today. I've been Ken Briota, Editor-in-Chief of Embedded Computing Design. This has been Embedded Toolbox, and you're all marvelous. We'll catch you next time.